We spent a couple of lectures writing proofs and coming up with all of this new notation, so, I think it's time we took it for a spin. Let's talk about searching problems. I guess you're hearing that and you're like, wait a minute, weren't we already talking about searching problems? A lot of the algorithms we've already covered were just variants of searching algorithms, weren't they? Yep, okay, I admit it pretty much. And actually, I'm willing to admit also that after this lecture, we spend a lot of the course covering various forms of searching problems. Okay, so actually what I want to do today is I want to talk about some search techniques that you've already seen in previous courses, things like linear search and binary search. I want them to have their day in the limelight. And even though it's good to take a break from all that notation and design algorithms again, I'm actually going to write a bunch of proofs in this lecture too. So even though you've seen linear search and binary search, let's say in first year programming, maybe you've never seen a proof of why binary search is fast and what really the insight behind binary search is, because binary search itself is a design technique that can apply far beyond searching an array. And that's why I want to start off with this scale. So I have this scale, and on the left-hand side, I've got some unknown weight. And the goal of this problem is to figure out how much this thing weighs. Now you might look at this and say, this looks like the beginning of a contrived setup, and you are right. And in fact, we're going to bring the scale back a couple of times in this course because it does give us a nice way of talking about a problem in a very abstract way. If I just talk about searching arrays, then we get really bound up in the way that data and computers work. And I just want to talk about solving a problem. And the scale gives me a way of doing that, taking a step back and talking about the problem in an abstract sense. Really, the algorithm I end up designing for this problem could be executed with no computer at all. It could just be a description of a good procedure for determining this unknown weight. All right, so all I will tell you about this weight right now is that the weight is an integer. So the value, whatever mass this thing has, is some integer. And it is between 1 and n. So it could be 1, it could be n, it could be any integer in between. And the problem that we have to solve right now is we're given this stack of labeled weights. And the reason I say labeled is because the idea is if I take the weight that's labeled 3 and I put it over here and the scale ends up balanced, well then because it says 3 on it, it's pretty obvious that that means that this thing weighs 3. So you're given this stack of weights, every value between 1 and n, and your task is to find one weight, find a weight, which balances the scale. And to be clear, for this version of the problem, you are only allowed to attempt to weigh one thing at a time. So there are all sorts of clever lateral thinking puzzles where you try and figure out what the fewest weighings required would be based on being able to put multiple weights on the scale at a time. But these antique scales break very easily, and I don't want you to break my scale, so I would like you to only use one weight at a time. But don't worry, we're going to come back to the scale a couple of times in the course, and we will get our turn to try putting multiple weights on the scale. We'll also see other restrictions of this problem, and we'll discover that actually the scale gives us a great way to model problems ranging from problems with really easy, simple and fast solutions. And the one we're going to see today has some simple and fast solutions, all the way up to these problems we'll see later that are actually very difficult, where we don't really know of any fast algorithms to solve them. All right, so I have this and I want to solve this problem and I want to develop an algorithm for it, and I want to be able to assert that my algorithm is correct and ideally come up with a fast algorithm. Now, before I do that, I want to formalize this problem mathematically. So just to clarify what I mean here, I think this problem description is very clear. I think it's really obvious what we need to do. The restrictions are built into it, so you can only use one weight at a time. You want to find one weight that balances the scale. The weight itself is going to be between 1 and n, whatever. I want to formalize it mathematically because I want to be able to talk about the process of weighing something without having to write the English sentence, pick up a weight, go over to the scale, put it on the scale, and read off the result, because that's going to take too long. I want some crisp mathematical way of talking about that. I also want to make sure the restrictions are very clear to all of us. Okay, so the first restriction, I want to balance the scale with one weight. And that's it. I can't put a combination of weights on there, but I have access to weights, to single weights that represent every possible value. So there shouldn't be an issue where I don't have the weight that I need. And the only way to test a weight is by putting it on the scale. And this, frankly, is because I know that, many of us, maybe all of us, are already thinking about clever ways to subvert this exercise. At least when I was a student, whenever I saw somebody present me some bizarre, contrived abstraction on some common task, I was like, okay, this is ridiculous. This is a waste of my time. What can I do to break this? So just so we get this out of the way, no, you are not allowed to pick up the gray weight and go somewhere with a digital scale and weigh it there or whatever. You can't put it in water to measure its density. You have to leave it on the scale. The only operation you are allowed to perform to investigate the weight of this thing is by weighing things on the other side of the scale. That is it. There's no other options. The only thing you can do to test it is by putting it on the scale. Good, we've got that out of the way. Now, how do we model the operation of using the scale? So one observation I will make here is that this is an old-fashioned balance scale, and the thing on the left is unknown. So I really have no right to read in at all to exactly what it means when when a particular weight k comes back being too light, besides, of course, that k is too light. So I really shouldn't be saying, well, okay, the distance between the two parts of the scale is x, and so that might mean that k is like half the weight on the left. No, I shouldn't do that. The weight k is either too light or it's too heavy, or the scale is actually balanced. Those are pretty much the only three states that I should be allowed to evaluate. And so we can model the result of actually putting a particular weight on the scale by inventing ourselves a function called weigh. And the idea behind the function weigh is it takes an integer k and just tells you, did the scale show light, heavy, or balanced on this? And so the function weigh evaluates to one of three states. And we're going to view these states as formal things. I mean, if you were to implement an algorithm to model this thing or implement it in code, you might say, well, okay, we'll define light to be the number -1, balanced to be 0, and heavy to be 1. Okay, whatever. For the sake of this example, it's sufficient to simply say that there are three states: light, balanced, and heavy. And so now we have this, I guess, much crisper and more symbolic description of the problem. We no longer actually have to draw the scale to be able to evaluate this function weigh, and we can begin, using this function if we design pseudocode or whatever. So the input of the problem is an integer n, so that would be the limit of the range of possible values, and the function weigh. I've written this so that the function weigh is sort of provided from outside, because that way it's not really your problem to wrangle the evaluation of that function into your implementation. We can just treat it as something that already exists. And as we'll see in a couple of minutes, I am going to argue that the function weigh can be evaluated in constant time. That is, the process of going over to the scale, putting a weight on the scale, and reading off the result should take the same amount of time regardless of which specific weight I've put on the scale. And the problem specification also requires that this problem only makes sense. An input is only valid if the weigh function behaves in a manner that matches the behavior of the scale, which is to say that there is exactly one weight that is correct. We'll say that that number is called W. Of course, you don't know what that is. It's your job to figure that out. But to be clear, there is only one value for which the weigh function returns balanced, and that if you pass in any value that is lighter than that weight, so W is the unknown weight, if you pass in a value k which is less than W, the scale always evaluates to light. If you pass in a value k which is greater than W, the scale always shows you heavy. And your job is to find, as the output of the algorithm you create, the single integer W in this range such that the scale shows that it's balanced. All right off the bat, here is an algorithm that I claim solves the problem. I've gone ahead and called it balance linear because I think at this point we can glance at this and sort of agree it probably is a linear time algorithm. And so the idea behind this algorithm is that we try every possibility. So there are n possibilities, 1, 2, 3, 4, 5, and so on up to n. We just try each one of them in turn, and we're guaranteed that one of them is going to be correct, and so when we find it, we return it. Interestingly, in the worst case, we actually still will never get to the bottom of the loop. We will always return, I guess you could say return early, return on line 4, because we will eventually find the correct weight. And so, because the solution is guaranteed to exist, we know this algorithm will be correct. I'm going to come back to what I just said in a few minutes, that brazen assertion that the algorithm is correct without providing any further justification. So it's reasonable to assume that the weigh function itself is constant time, and that means that everything inside the loop is also constant time, and that means that the only thing dependent on my parameter n, as far as the running time is concerned, is the number of iterations of the loop, and it's pretty obvious from the structure of the loop that that is n. And so I'm going to claim that the solution here is big theta of n. One thing I'll observe, and this is part of the idea of abstracting this problem, is that this parameter n is not actually the input size It's just some property of the input. Normally, when we talk about the running time of an algorithm, we want to couch it in terms of the size of the input, but that hasn't really happened here. Although you could argue that n is the size of the range of possible values. So in a sense, n does describe a sort of size parameter on the problem, just not a traditional one. It's also true that what we're building up to is the binary search algorithm here, and that we often apply binary search on arrays or sequences, where, of course, the size of the sequence is the parameter that we care about when we're measuring the running time. But for the sake of this abstraction, n is just a value that's been passed in from outside as a way of describing the range of values you have to consider. By the way, a minute ago I said this was constant time, and then I said the algorithm itself was linear time. And I've done this before. We did this in the last couple of lectures, but just so we know, it tends to be the case that people would like to, when they write something down in text or when they talk about it in sentences, they would rather not read symbols. And sometimes reading the symbolic name of a running time is a bit verbose. So when I'm having to say big theta of 1, well, it's a lot of syllables, and I use a lot of syllables on a day-to-day basis, so I'd rather not waste them. So I might say constant time. And I often also say linear time instead of big theta of n. And I occasionally find myself talking about exponential time. And to be fair, exponential time is actually not just 2 to the n. It might be 3 to the n or 4 to the n, or anything where n is appearing as an exponent of a constant base. If we see weird situations like this, that is, I don't know what we'd call that. I don't know if it would be fair to just call that exponential time. And so exponential time often just refers to the general case where n is an exponent. I also occasionally talk about polynomial time. That'll come back at the very end of the course when we talk about the idea of an algorithm being polynomial, which is n to some power, versus exponential, which might be 2 to the n or whatever. It is also true, though, that we can go overboard with this, and that there are people that want to refer to every algorithm complexity in using an English phrase. And I don't tend to buy that. So, of course, I'm pretty pragmatic about this, as with anything else, which is that if the goal of talking about algorithms is communication, which I believe it is, then we should choose a communication strategy that is as clear as possible. And there are times when coming up with more vocabulary does not make things clearer. So saying linear rhythmic in particular is something that you probably won't catch me doing, because I could just say big theta of n log n. I know that's extra syllables, but how do I know that everybody I'm speaking to knows the word linear rhythmic? And more generally, there are lots of other algorithm running times I could come up with, and if we have to make up an English name or use Latin and Greek to mash together words to come up with a name for it, eventually we're just memorizing useless vocabulary. There are a lot of functions that appear in running times in some cases that we may not ever see, where I don't even know what English name we would use. So, for example, there are occasionally algorithms that have running times that are log of log n. And I mean, what do you call that? Logarithmic or something? I don't know. So we could just say big theta of log n or big theta of log n. And there are also all sorts of other weird constructions where, again, you can always read off the big theta expression. So the question then is, can we do better than linear time for this problem? And I mean, that's a natural question. And one thing I want to get at in this lecture, something that we don't see very often in this course, but something we have to get at eventually, is when am I done? When can I safely stop in trying to improve my algorithm? So here I've come up with an algorithm that is linear time. It takes at most big theta of n time to tell me what the correct weight to balance the scale is. And often it's the case that you design some algorithm to solve a problem and it's too slow. And that's a good reason to go looking for a faster one. It's often also the case you design an algorithm for a problem and you feel like maybe, even if it isn't too slow for practical purposes, you feel like you could do better. And of course, that's a good reason to go looking as well. One thing to consider is that we talk about algorithms theoretically in this course, but in practice, it's always a matter of balance. And it's also a matter of balancing the amount of time you want to spend on something versus your assessment of the possible payoff. That is, if you try improving this algorithm and spend 2 weeks doing it and you manage to save 5 operations, that might not have been worth it. So, of course, in practice, what you typically do is you design an algorithm to your satisfaction, and then maybe you go and implement it or use it or something, and only if you decide that it's way too slow do you go back to the drawing board. Often when you design an algorithm, you have some intuition as to whether it's going to be too slow. So if you get an algorithm that is big theta of 2 to the n, and you know that you're working with inputs where n could be, some massive number, well then, of course, that's a good reason, without even implementing it, to know that you might need to do better. Linear time is usually considered to be pretty good. So the question, can we do better than linear time for this problem, is one we are going to consider here, but keep in mind that in practice, you could often be content with a linear time solution. But there is that question, when am I done? Suppose I find a log n solution, which it turns out I will. Is that the fastest I can do? It's certainly true that it's not like every problem has a constant time solution, right? So there has to be some limit on how fast I can make an algorithm. And occasionally we have the chance to prove that. We'll see later that it is actually possible to prove for certain search problems that a linear time algorithm is the best you can do. So if you come up with a linear time algorithm, that's it. You can't get any faster than that, at least asymptotically. So can we do better than big theta n for this problem? So I guess the question is, what is my intuition? And if we look at this, are there any things we can see that give us a hint that maybe we can save some time? We don't know whether the amount of time we can save is going to be an asymptotic improvement. So an example of that situation is, consider back in the first lecture, this ongoing contains duplicates saga we've been working with, where I observed with our basic nested loop algorithm, there was that case where index I might refer to element 6 and index j might refer to element 187. And in the basic algorithm that I proposed in the first lecture, there was also a step where j would be on 6 and I would be on 187. So this pair of things here got considered twice, which seems inherently sort of wasteful because nothing would have changed between each consideration, and there's no real significance to which thing is first and which thing is second. And so I said, well, why don't we just consider each pair only once? And we could save half of the work. And we did, and we discovered that it did save somewhere around half of the work. But the problem was it didn't lead to an asymptotic improvement, because if I divide the amount of work, the amount of work goes from n squared down to n squared over 2, all I've done is multiply the amount of work by a constant, which of course doesn't take us out of the asymptotic class big theta of n squared. But certainly if I find some places where too much work is being done, or where I'm not fully exploiting the features of the problem, that's a hint that maybe I could improve my algorithm. And then I have to hope that my improvement actually leads me to an asymptotically faster algorithm. There's a couple of things I can observe about this one. So one of them, which is sort of subtle if you look at the pseudocode, but I'm sure if you hear about it you'll agree, is that we are not actually seeing all of the possible states of the scale. So I count up from 1. I try 1, then I try 2, then I try 3, and so on until I find the correct one. I know I'm going to find the correct weight eventually. If I try 1 and it's too light, then I move on to 2, and I rule out one possibility. If I try 1 and it doesn't work, well, then I can rule out 1 as a possibility. I just said, suppose I try 1 and it's too light. Is there ever going to be a case where I try 1 and it's too heavy? Well, obviously not, because if 1 is too heavy, then so is everything else. Okay, so put a bookmark there for later. Additionally, suppose I try 1 and then I try 2. Is it possible that 3 is going to be too heavy? Well, no, because 3 will either be too light, in which case I keep going, or 3 will be the correct weight, in which case I'm done. So you might notice that actually, at no point during this sequence do I ever encounter a weight that's too heavy. I just I just cross off all the weights that are too light until I hit the one that's balanced. And so the scale, the way function, gives me the option of checking whether something's too heavy, but I never exploit that. There is a sign that there might be some depth to the problem that I could exploit to improve my algorithm. Another big thing that jumps out at us, which I just foreshadowed, is suppose that I start by considering, I don't know, the value 4. Okay, and then, I have all these other values up to n. Suppose I don't bother with 1, 2, or 3, I just worry about 4. And I discovered that 4 is too heavy. What does that tell me about all the other inputs, about all the other possibilities? Well, if 4 is too heavy, then 5 is going to be too heavy as well. And in fact, everything between 4 and n is also going to be too heavy. So I can just ignore them. And by testing just the number 4, and being lucky and having it come back as being too heavy, I ruled out almost every possibility. That's a pretty big deal. Now, of course, what if I wasn't so lucky? What if 4 came back and it was too light? Well, I can still rule out 1, 2, 3, and 4, but that's not as dramatic as ruling out everything between 4 and n, because, n could be 100,000 or something. So interesting. So if I try a weight more or less in the middle, then I might be able to rule out a lot of other possibilities. Now, I don't know in advance whether the thing I try will be too light or too heavy, so what's the best one to try to be magnanimous? Well, I think the best thing to try there might be the thing actually in the middle. So this observation, I guess I got behind on the slides, is if I try a particular weight k and it's too heavy, then that means that weight k plus 1 and k plus 2 and everything up to n are also going to be too heavy. So what I could try doing right off the bat, instead of starting by weighing 1, I could start by weighing n over 2. And I should add a note here, maybe you can consider that actually n over 2 might not be allowed, because suppose that the value of n is, I don't know, 9. Well, okay, so that means that n over 2 is 4.5, which is not an integer. So I can't use non-integer weights. Bear with me. I will address that in a minute. Just for the sake of intuition, we're just going to say n over 2 here and understand that we mean, the closest weight to n over 2. Suppose that I start by weighing n over 2. Well, if n over 2 comes back being too heavy, then I can rule out everything greater than n over 2. That's about half of the remaining possibilities. If n over 2 comes back to be too light, then I can rule out everything less than n over 2, which is again about half of the possibilities. So this gives me a way of wiping out a huge number of possibilities with just one use of the scale. So let's try that out. What I'll do at each step is keep track of the limits of the range of values that I know are possible at this point. So at the beginning, the value could be 1. It could be anything between 1 and n. So my range is 1 up to n. And so I'm going to try n over 2. Okay. So, and then I do that. I discover that n over 2 is too light. So if n over 2 is too light, then everything between 1 and n over 2 is also going to be too light. So every weight less than n over 2 can be eliminated as a possibility. So I could update my minimum to be n over 2. Now you might also be staring at this and saying, hey, wait a minute, actually n over 2 is too light, so there's no way n over 2 will be the right answer. Yes, that's right. It turns out the minimum should be n over 2 plus 1. But again, with the interest of keeping the numbers clean, for now I'm just going to leave it and say n over 2. There's nothing wrong with having the range be a little bit too big, but we'll see later that yes, I actually can make the range a bit tighter than that. So we'll come back to that when we come to writing the pseudocode. Okay, so now I've ruled out half of my possibilities. So what do I do next? Well, what I could do is just repeat the same process. I could now try doing the midpoint of n over 2 and n, which would be 3n over 4, which I think the slide agrees with. There it is. And we discover, suppose, that 3n over 4 is too heavy. Well, if that's the case, then everything greater than 3n over 4 is also too heavy, so we can rule all of those out. That is half of the remaining possibilities. So now I've managed to rule out half the possibilities on the first weighing, and then half of the remainder, or 1/4 of the original number of possibilities, on the second weighing. Okay, so I just keep going. I keep trying the midpoint. And so here I try 5n over 8, and then that comes back too light, which means that my new minimum is going to be, after the end of this step, it's going to be 5n over 8. And so at each step, I'm ruling out half of the total possibilities, and intuitively at least, so this is not making a formal statement, what's written here, it's making an intuitive statement, what we can expect. Since each of these trials rules out half of the remaining possibilities, I think it's reasonable to expect that we can get the right answer faster than in the linear time algorithm where we just tried each weight in sequence. Now, it's one thing to expect that, it's another to demonstrate that it's true in all cases. And another still to demonstrate that it's faster to an asymptotic extent, that doesn't still come back being big theta of n. Those are things that we have to prove. So here's some pseudocode for that algorithm. And so what I have here is we start with two variables high and low to refer to the endpoints of our range, which of course at the beginning of the algorithm will just be every integer between 1 and n inclusive. And then I'm going to keep narrowing the range down. So maybe I narrow it down so that it's, let's use a concrete example. So suppose I do my range is 1 up to 10. So I try the value 5. And suppose that it comes back and 5 is too light. Well, if 5 is too light, then my range actually gets narrowed down from between 6 and 10, because 1, 2, 3, 4, and 5 can be ruled out. Okay, so now it's 6 and 10, so I try something in the middle. Suppose that I try 8. And if 8 comes back, let's say 8 is too heavy. If 8 is too heavy, then my range gets reduced to 6 and 7. Okay, and then suppose that I try, 6 to 7, there's only 2 values available. Suppose I try 6, and then I'm lucky and it turns out the answer is 6. Okay, great. So I was able to get it down to a range of size 2 pretty quickly. But in the worst case, I might reach a situation where suppose 6 isn't the right answer. Well, in that case, the range is going to be 7 to 7. And you can see here the lower bound equals the upper bound. So low equals high. So the idea here is my loop is going to keep refining my range over and over again as long as low is less than high. Eventually, either we find the correct weight, which would happen at line 12, or low equals high and the loop can end. There's no need to refine the range further. And of course, I'm going to come back to this a few times in this lecture, so that's just a brief summary. At each step, I compute the midpoint of my range. We'll call that k. You notice I've used the floor function here, and that's really the way I'd implement this in code is I would use integer division. Generally, I don't write code involving the floor function unless I'm working with floating point data, which wouldn't really make very much sense here because I have integer data for everything else. But I've used the floor function here because we're going to need to write a proof in a little while. And in the proof, where we make mathematical statements, the floor function is meaningful, whereas integer division, generally mathematically, is represented with the floor function. Okay, so at each step on line 5, I compute the midpoint to the extent possible, so rounding that number down to an integer if necessary, the midpoint of my range. And then I try weighing that value. So I evaluate the weigh function. And if it comes back being too heavy, if I weigh k and it comes back being too heavy, so let's just take a look at a hypothetical range here. If I decide that k is too heavy, well then my range definitely, everything from k on up can be omitted, which means my new range can actually be 1 up to k minus 1. Because k minus 1 is the largest value that's still in play. Similarly, if I weigh k and it comes back being too light, well then I can assume that everything up to and including k is ruled out, and so my range now starts at k plus 1. One quick note. So here, notice how it says, okay, try weighing k and see if it's too heavy, and then else, weigh it again and see if it's too light. I'm going to treat this as if this entire if statement calls the weigh function only once. It doesn't really make that much of a difference, but just to be clear, I think I can do that because obviously we could store this in a variable or something. It's just easier mathematically to talk about it by putting the full expression in each condition. There's a third case, which is suppose that it doesn't come back heavy and it doesn't come back light. Well, then I have this else, and of course there are only 3 states, which means that down here the scale this is the case where the scale is balanced. And if the scale is balanced, then I guess I'm in luck, and I just return the value of k. That's the answer. You might already know, we've seen this in the previous lectures, we might already be clicking into the idea that, okay, this is probably not going to happen in a worst case input. In a worst case input, the loop just keeps going and going as long as it possibly can. We can't expect to be lucky. And then eventually, if we're not lucky and we don't return sooner, we get to a point where the range is so small that low and high are the same number. In which case, since they're the same number, we can just return low or we can return high, and that will be the correct weight. Now, I've got a lot to justify here. Before I do any of that, let's do an actual example to show the pattern of this algorithm as we walk through a particular example of W, of the ultimate unknown weight. So suppose that n equals 100, and I tell you there is some weight W. I won't tell you what it is, but you have to figure it out, and you can use a scale to do that. So n equals 100, and we're going to use this improved algorithm. And so we start off with low being 1 and high being 100, and the very first thing we weigh is 50. Because, of course, if we take the average of 100, well, that's going to be equal to 50.5, but then the floor function takes care of that 0.5 for us, and we just get 50 again. So I try to weight 50. I determine that 50 is too heavy. And that means everything between 50 and 100 is now ruled out. And so my new high is going to be 49. Okay, so 50 is too heavy, so I set high to be 49. And now I try the midpoint. Okay, so 1 plus 49 over 2 is equal to 25. So I try weighing 25. There it is. And I discover that 25 is also too heavy. So my new upper bound, my new high, becomes 24. Okay, so now let's see. 1 plus 24 over 2, well, that's going to be 12.5. But again, we can just call that 12 because we need an integer. So we weigh 12. 12 is still too heavy. So our new upper bound becomes 11. And then we try 6, and 6 is too light. So our new lower bound becomes 7. And just to recap here, so we weighed what? We weighed 50, okay, that's 1, 25, that's 2, 12, that's 3, and then 6, that's 4. So in 4 weighings, I was able to get the range down to 7 up to 11. So that's a range of size 5. So I was able to go from 100 possibilities to 5 possibilities by using the scale 4 times. So I think I'm onto something here with this idea that this algorithm could be faster. But let's follow it through. Okay, so I now try weighing the midpoint of 7 and 11. I get 9, and then I weigh that. 9 is too heavy. So 9, 10, and 11 are now out of the question, and my new upper bound becomes 8. Okay, so now I'm down to a range of only two possible things. But the algorithm still continues because low is still less than high. And so I compute the midpoint. So 7 plus 8 all over 2 is going to be, well, 15 divided by 2 is 7.5. Getting rid of the 0.5, I get 7. So I try weighing 7. 7 is too light. Okay, so the algorithm at this point says, well, set your lower bound to be k plus 1. Set it to be 8. So now low equals high. There's only one possibility left, and it's 8. And that means I'm done. I don't actually have to put 8 on the scale because I know that since you guaranteed me that there was a right answer and I narrowed down the possibilities to one option, by process of elimination, 8 is the answer, and that's it. I don't have to bother putting 8 on the scale to prove it because I know it to be the case. It's not actually necessary to test weight 8. So only 6 trials were needed to determine the correct weight from 100 possibilities. That's a really big deal. On the other hand, how can we be sure that that generalizes? I mean, maybe I cooked up a clever example. Maybe by choosing the weight to be 8, I cooked up a clever example where for some reason the algorithm finishes quickly. Maybe this is just a best case input. And there could be some inputs where the algorithm requires 1 billion steps on n equals 100. So, of course, as we know, maybe I'm just making a good sales pitch. I mean, I claim to have designed this algorithm, and if I invented the algorithm, maybe I could design a way of selling it well. So it's up to me to justify that the algorithm is actually fast, and moreover, that the algorithm actually works. Now, maybe you can see the algorithm and think, yeah, okay, it probably does work in general, but it's not really your problem. If you have any doubts, it's up to me to try and put those doubts out of your mind, to try and convince you that the algorithm works. The extent to which I need to do that formally can differ depending on the problem, but we do have to ask this question. Does the algorithm actually work in all cases? All I've done is demonstrated to you one particular case. So when the weight is 8 and n equals 100. What about every other value of w? What about every other value of n? So it's my responsibility, if I'm the algorithm designer, to justify the correctness of the algorithm, to provide what's typically called a proof of correctness. And you might look at that and say, but wait a minute. We've already talked about a bunch of algorithms. Where were the proofs of correctness for those? And I mentioned back in lecture 1 that we even if we're going to be completionists about this, we can't do everything. I can't show you how we can. I can't prove that 2 plus 2 equals 4 because if we spent all of our time proving everything before we could use any results, we wouldn't even be close to the point of studying algorithms yet. And so we have to compromise a bit. So here's the way I view this. From a practical point of view, yes, it's true. If you're a formalist, you would argue that no algorithm is correct until you see the proof of correctness, and therefore that all of the things I've discussed so far are just sort of intuitive sketches and not really algorithms because I did not provide you a written proof of correctness. It is useful to write proofs of correctness for simple algorithms just because that gives you practice in writing proofs of correctness. So if you went back and looked at our contains duplicate algorithms like the nested loop ones or sum array, you could write a proof of correctness for it. And when you did so, you would probably look at the result and say, this doesn't really help very much because the algorithm itself is self-explanatory to such an extent that the proof doesn't really enlighten anybody. It's just a bunch of notation. It's sort of needless formalism. And that's a bit of a difficulty. So it's true that, so I keep talking about this idea of formalism or being a formalist. To be clear, what I mean about that is that there are those that are able to sort of in their head justify a lot of mathematical conclusions. And I think all of us have that skill to some extent because we know enough about math to be able to understand lots of steps without necessarily needing somebody to break them down into pieces. That's fine, that's good. And it's also good to have proofs of correctness of algorithms that are complicated because we can't expect everybody to glance at something and be able to see all the way through all of the mathematical insight. And so we have to split the difference a bit. We have to give people enough credit that we don't try and write a proof of something that's dead easy for them to waste their time reading an unnecessary proof. But we have to be formal enough that we can understand which facts are controversial or which facts do need justification. So a so-called formalist is somebody that maybe doesn't want to make that distinction to the extent that I do. It turns out that over time I've become more formal in a lot of my things, probably because I have to teach classes, and I realize that if you want other people to understand something, you have to explain it to them. That's one argument for formalism, versus a more intuitive point of view, which is simply that as long as you can make sense of something, it doesn't really make much of a difference whether the explanation has been written down. So here's what we're going to do in this course. We are going to cover proofs of correctness because, of course, that is a necessary tool that you need to have on hand if you're designing algorithms. The only times I'm going to write a proof of correctness down as part of a lecture are cases where the algorithm I'm describing is somehow unusual, either because it uses a standard technique, maybe one that we already know, but for the first time, or because it does something completely bizarre. And of course, when an algorithm does something bizarre, you probably need to be convinced. And convincing you is basically writing a proof. So I'm going to write a proof of this, and I will add that the proof I'm about to show you is probably quite a bit more verbose than what we will typically write. And that's because it's the first one that we've seen. And we'll see later that we are able to condense down what we write once we realize what's important about a proof of correctness. And so an example of an algorithm for which I will not give you a proof is this one. As I mentioned a few minutes ago, I believe that this algorithm is self-evident. Its correctness is self-evident. The algorithm itself is somewhat self-explanatory. The pseudocode does a pretty good job of explaining to you why the algorithm works. I just try every possibility, and then one of them is going to come back with the scale being balanced. And that's it. Writing a proof of this, I could use induction or a technique like what we're about to use. You'd read that proof and say, wow, that was a big waste of 10 minutes. There's, in 30 seconds, you could gain more by reading the pseudocode than you could out of reading my proof for 10 minutes. On the other hand, this algorithm, this improved algorithm, maybe you see the insight behind it, but even so, we want to have somebody needs to write down why this always works, why there's not some case hidden in there somewhere that we don't notice that causes this procedure to break. And of course, who has to convince people? Well, it's me. I'm the designer of the algorithm. So I guess I'm proving the theorem here, that this improved algorithm does solve the problem. Now, it's a different question as to how long it takes, but for now I want to prove that it solves the problem at all. So to prove correctness, what I have to establish simply is that if you give me a valid input, an input that meets the criteria, I always give you the desired output. So the output here is I give you the value W where the scale comes back balanced. I now have to prove that indeed that the scale does come back balanced after I've run the algorithm. That actually there's a quirk to that, which is not only that I have to prove that the return value is the right value, but also that the algorithm does return something. I mean, imagine a situation where this loop ran forever. If the loop ran forever, the algorithm would never return anything. So you couldn't argue that the return value is incorrect. But unless there is a return value in all cases, it's not really an algorithm for this problem. And I'll add that there are lots of algorithms where we don't bother proving that it terminates. Like this algorithm here, not only is it simple, but this loop, it's very easy to justify that this loop terminates because the loop counts up to n, and n is a finite number, and it's a counting loop. Versus this loop, which is a while loop on a condition that's a little bit non-trivial. Like it's sort of clear that it has to terminate, but there is still some room for doubt, and so we have to prove it. Okay, so the first thing I want to do is I want to establish that this process of narrowing the range down actually makes sense. So what I was relying on, if you tell me that the weight is between 1 and n, what I take that to mean is that this unknown value W is somewhere between 1 and n. And the goal of my improved procedure is to narrow the range down, but at all times ensure that the actual value of W is still sandwiched between my values of low and high. So if, for example, I discover that n over 2 is too heavy, well then I adjust the high end of my range to be something like this. What I want to prove is that at all times this statement is correct. Let's say, well, not necessarily at all times. Every time I evaluate the loop condition. So what I'm stating essentially is that this statement is an invariant with respect to, how about line 4? Every time I hit line 4, this holds. And the idea here is that if I can demonstrate that low and high always have W sandwiched between them, then later if I can demonstrate that low and high keep getting closer together, well then it's true that if by the time that low and high are equal, W has to equal both of them. And so the technique I'm using is the technique of using an invariant to prove the correctness of the algorithm. And what I'm going to do is show that this statement holds at the beginning and end of each loop iteration. Although really, to do that, I only have to show that it holds at the beginning because the thing right after the end is the beginning and nothing changes in the meantime. So what I'm going to show is on line 4, every time I evaluate this loop condition, this statement is true. This holds. The unknown weight W is in between low and high. Observe that W isn't actually used anywhere in this code because, of course, W is the answer that you seek. If you had it, you just return it. I'm still allowed to reason about the behavior of W even if I don't have W in front of me. So here's the claim. Every time the loop condition is tested, this invariant holds. This is actually, the claim is that this thing is an invariant with respect to line number 4. And I'm going to prove this by induction. Because it's easy with induction to start by proving that it holds the first time I run the loop. So the first time I hit line 4, it's easy to establish that the invariant holds. And then I can use the inductive process to show that if it holds at one iteration, it must hold at the next iteration. So I'm going to use induction on the number of iterations of the loop that have been executed so far. Again, I will observe that nowhere in this algorithm does it count the number of iterations of the loop. There is no variable I, but I'm still allowed to think of the number of iterations that have occurred and count them if I need to for the sake of the proof, so I'm going to do that. So I is the number of iterations that have already occurred. So when I equals 0, that means that no iterations of the loop have occurred. In other words, that I've arrived at line 4 for the very first time before actually iterating at all. And that's my base case. So the basis for induction is before the very first iteration, well, in the pseudocode it's pretty clear that low is 1 and high is n. And in the problem specification, we were explicitly told that the weight W is between 1 and n. And so that means that the invariant holds. And so I have my basis. Now I state my induction hypothesis. The induction hypothesis is, suppose that this invariant holds for every iteration up to and including iteration I for some value of I greater than or equal to 0. Now notice, because you know I'm a stickler for this sort of thing, that this statement of the value of I does include the value in the basis, as it should. Notice also that although it's not that obvious, I mean, it's there, but it's a bit subtle, this is actually what we might call a strong induction hypothesis. In your previous course, like a discrete math course, when you were taught induction proofs, you probably had to differentiate between so-called strong induction and regular induction. And you would say at the end of the proof, by strong induction, this thing holds. The idea behind a strong hypothesis is that it states that the claim that you're trying to prove holds for a variety of previous cases, not just one of them. So a couple of notes about that. First, it turns out I actually don't need a strong hypothesis for this. I only need it to hold for one iteration to prove that it holds for the next one. However, when I wrote this up, I figured I always write it this way, so I'll just write it this way again. There's no harm in stating a stronger hypothesis than you need, and it turns out it works just fine if I do that, so I chose to do it. Also, unlike in a course where you're working, when you're writing proofs about a lot of numerical things, and to be clear, this proof does hinge on a lot of numerical properties like the values of I, we are often going to find ourselves in this course writing induction proofs about discrete structures, so things like trees and graphs, for which it isn't really obvious or the line gets a bit blurred between what is a regular induction hypothesis and what is a strong one. And so, in this course, I'm just going to call them both induction. That is, the strength of the hypothesis is up to you as long as you're able to prove the claim. You don't have to tell me whether it's a strong hypothesis or a weak one, as long as you write whatever hypothesis is necessary to prove what you want to prove. I'm going to do that here as well. At the end of the proof, I'm going to write by induction. Who cares if it's strong induction? All I care about is that the proof is correct. So suppose that the invariant holds for every iteration up to and including iteration I for some iteration number I greater than or equal to 0. Now, what I aim to prove here is the induction hypothesis told me that as of iteration I, the invariant held. So in other words, when I'm at iteration I, at this step of iteration I, the claim holds. We have our invariant. All I have to show now is that nothing that I'm doing down here breaks the invariant. Or more generally, by the time I get down to between line 13 and 14, the invariant holds again. It is valid, although I don't think it happens in this algorithm, it is valid for the invariant to be temporarily broken in the middle, as long as by the time I get to the next iteration, the invariant holds again. So because of my hypothesis, I know that at the beginning of iteration I, the invariant held. So I'm allowed to assume that that was the case, and then all I have to do is show that whatever I did during iteration I didn't break the invariant. So during iteration I, the value of k determines the path of control. Now, I guess I omitted the floor function there. That's not going to be too big of a deal, but and we're going to see the floor function causes us some grief later, but we should appreciate that the effect of the floor function is very minor. The worst the most by which it can modify k is is within a radius of about 1. Okay, so I get my value of k, and then three things can happen. These are just the three cases of my if statement. So if k comes out to be too heavy, well, what that's saying, if k is too heavy, is that the real weight w is strictly less than k. And so what we're observing is because this invariant already held, we've got low, and then low is less than or equal to w, which is less than or equal to high. And we also know that k is less than or equal to high, and that if w is less than k, well, that means that w, because it's an integer, has to be less than or equal to k minus 1. So in the case where k is too heavy, we get this. W is less than or equal to k minus 1. And we then set high to be k minus 1. So the new value of high is k minus 1, and that means that at the end of the iteration, the invariant holds. Okay, good. If, in case number 2, if k comes back to be too light, well, if k is too light, that is the statement that k is less than w. And if k is less than w, then k plus 1 is less than or equal to w. And then that in turn is less than or equal to high. And because I set low to be k plus 1, my invariant holds at the end of this iteration as well, because the new value of low is k plus 1. Okay, so in both case 1 and case 2, the invariant does hold at the end of the iteration. Those are the important cases, frankly. There is a third case. So if we look at the pseudocode, I mean, we do have this situation here. And so you can see if k is not too heavy and not too light, okay, well, that means that k has to balance the scale. And that doesn't really hurt us, but we do have to address it. So let's talk about that. So if the wave function gives us back the result balanced, well, then k is equal to w, and we're done. We just return the value of k. That's it. And what's neat about this is that there is no iteration I plus 1. So who cares? Like, it doesn't make any difference because the algorithm already ended. We only have to talk about iteration I plus 1 if there's a chance it could actually happen. So what we do is basically say, well, okay, case 3 is all well and good, but it has no effect on the outcome. Assume that case 3 didn't happen, because if it did, we're already done. So in cases 1 and 2, the invariant holds at the end of iteration I, and therefore continues to hold at the beginning of iteration I plus 1. In case 3, it makes no difference because we don't get to iteration I plus 1. Therefore, we have proven that if the iteration holds at the beginning of iteration, if the invariant holds at the beginning of iteration I, that it must hold at the beginning of iteration I plus 1. And therefore, by induction, by putting all three parts of our proof together, we have shown that the invariant holds every time the loop condition is tested. Okay, so if we skim back over what we had here, it turns out that if I write a proof of correctness based on this idea of an invariant, specifically a loop invariant, pretty much all proofs of that sort, if I write them in a full induction style form, look like this. So my basis is just at the beginning of the loop, it holds. My induction hypothesis is suppose that it holds at one iteration, and my induction step is now I'm going to show you that it holds at the next one. Because this is so common, it is often seen in many sources, including what we're going to see later in the course, that we write loop invariant proofs without all of the induction infrastructure. We don't bother writing basis, hypothesis, induction step. We write them in a compact form where we simply say, suppose the claim holds at the beginning of one iteration, we're going to show it holds at the beginning of the next one. And that's completely valid. It's not valid to condense induction proofs in general, but when you know you're writing a specific kind of proof, if I tell you this is a loop invariant proof, you know what to expect, so I can leave out some details. But I showed the full version here just so that we know what we're working with, so we all know the baseline for this kind of proof in the future. Here's another claim that I sort of have to justify. And I thought a lot about this before I started recording this, and I want to cover this extra bit of proof, but I want to make it clear, I'm doing this for completeness, to show a thing that we often take for granted, but what we should be appreciating and shouldn't be taking for granted. However, it is true that in practice, you probably don't need to provide this step. Maybe some people watching disagree, that's why I'm providing it anyway, but later in the course, we won't bother with this next step here, and I'll explain why in a couple of minutes. So the claim here is that this algorithm does always terminate. There is no infinite loop, and indeed that when I finally hit the return statement on line 16, the value I return, which is just my variable low, actually is my unknown weight w. I'm going to establish that fully. And so here is a wall of text describing that, just for completeness' sake. So at each step of the loop, either the algorithm terminates, and of course we're proving that the algorithm always terminates, so obviously if it does in the middle of the loop, that's good. But suppose it never terminates in the middle of the loop. Okay, so the loop just keeps going as long as it can until the loop ends of its own accord. Well, how does that work? Well, the difference, high minus low, that is sort of more or less the size of the range, although the actual size of the range is that plus 1, the difference between high and low always goes down by at least 1. In other words, we're never going to have a situation where we've got low and high at one iteration, and at the beginning of the next iteration, they have not changed. Because, of course, if we had that problem, then the loop would go on forever. It would be an infinite loop, because it just keeps going around and around in a circle. I can prove that at each step, either high goes down by 1 or low goes up by 1, or the algorithm ends for some other reason. And if that's the case, that means they have to keep getting closer together. And that means because the loop condition, which is low is less than high, because that loop condition is equivalent to this statement here, then eventually, if they keep getting closer together, if this difference keeps going down, well, eventually the difference is going to hit 0 and the loop will end. Okay, so there's that. And so just to make sure we have that justified, during the loop, we use this value k to adjust either low or high, unless, of course, we terminate for some other reason. Now, this is the part that I said, this is actually probably unnecessary formalism. I think we can expect that somebody reading our pseudocode would be able to put this together, but just in case they can't, here is how we would demonstrate this fact. So what I want to show here is that the loop keeps approaching the state where low equals high. The condition is that low is less than high. And somebody that's really skeptical could argue that when the loop finally ends, maybe low is greater than high. And if that happened, that would make a real mess of our algorithm, because if low is greater than high, then what is W? It turns out that our earlier invariant proof sort of rules this out, because when the loop condition is tested, low has to be less than or equal to I, which is again why this is unnecessary formalism, but we're talking about it anyway. If I want to assert that we're never going to be in a situation where low is greater than high, what I can do is observe that K is used to set the value of low and the value of high. So I set them based on K. And I can show that because low is less than high at each step, low and high have to be separated by at least 1. I can show that, of course, low is going to be less than or equal to k, because k is the floor of high plus low over 2, which has to be greater than low plus low over 2, because low is less than high, and has to be less than high plus high over 2. And therefore, that when I set either low or high based on k, the value I come up with will never be on the opposite side of, so I won't end up making high less than low, and I won't end up making low greater than high. So there's one way of establishing that. Oh, okay, so that was probably unnecessary given the other proof that we just wrote. And so therefore it has to be the case, based on our invariant and this extra justification, that by the time the loop ends, low has to actually equal high, and therefore it has to be true that low and high equal W, and so what I actually end up returning on line 16 equals W. Okay, so if you were a member of the formalist school of thought before all of that, maybe that was enough to change your mind. Even I'm becoming less of a formalist, having had to go through that. So to be clear, the proof of correctness that we typically write is essentially just this part of our first proof here, just to show that if I start at one iteration and the invariant holds, it must hold at the next iteration. For loop invariant proofs, usually that's enough, as well as some explanation, if it's not obvious, why the invariant holds at the first iteration. The secondary proof, which is just there for the skeptics, and it's the last time I'm going to throw them a bone, is showing that indeed the algorithm does terminate. There's a reason why we don't need this, beyond the fact that some of it's redundant with respect to our earlier proof, and it's the fact that we actually are going to end up analyzing our algorithm for running time. And so that's what this note is pointing out. Most of the time we design an algorithm, we analyze its running time, and we specifically analyze its worst case running time. And if I can tell you, if I can assure you, if I can prove formally, even if it's a big number like 2 to the n, if I can prove formally that the running time of an algorithm is never larger than 2 to the n, I can observe that for any value of n, 2 to the n is a finite number. And that means that if I ever have a question about whether the algorithm terminates, if the running time is a finite number, well then the algorithm has to terminate in all cases, because this is the worst case running time. So usually we don't bother proving the algorithm terminates as a separate step. We just do that as part of demonstrating the running time. Now it's true that when you prove the running time, you have to establish that the algorithm always finishes, because otherwise the running time is unbounded. But that is something we're used to doing as part of running time analysis. Okay, so there we have it. And actually, while we're on the subject, what's the running time? So I wrote here, what's the asymptotic running time? We're used to the idea by now that this means worst case running time of the algorithm. So what does it mean when you're asked this? Like, what's the expected outcome of what is the running time style questions? Well, ideally, we could, the best answer I could give would be a big theta expression for the worst case running time. And in this course, at least, because not every source uses big theta very much, Big O is very widely used, and a lot of sources use big O in a lot of ways that we might use big theta. But I like having both around because it helps us understand a certain semantic nuance between the two, between what we can say about the algorithm. I mean, we know the difference between big O and big theta, but how does it work when I apply it to a running time? When I tell you that an algorithm's running time is big theta of n squared, that is me telling you that there actually is a worst case input that requires n squared time, either because I can show you one or because I can prove that one has to exist. In other words, the algorithm is not faster than n squared. There is going to be a case where it does take n squared operations. So the best analysis, the tightest analysis I can perform is some that actually allows me to say the running time is n squared in some case, or better. It's better in every other case, but it's definitely n squared in at least one case. There are situations, and we're going to see some pretty soon, where we can't actually do that. The best we can hope to do is to show that the running time is certainly no worse than n squared, but we don't actually know whether it really takes n squared operations. It might take less. All we can show is that it definitely doesn't take more. That's where we might give a big O expression. So if I tell you this algorithm's running time, let's say t of n is big O of n squared. That's me telling you that it isn't any worse than n squared. I don't have a guarantee that it actually is n squared. I mean, for all I know, my algorithm could actually be big theta of a constant, because as we know, every constant is big O of n squared. So when I tell you that all I can do is give you a big O running time for an algorithm, really what I'm saying is that I can give you a guarantee that it's no worse than that. And for worst case analysis, that's often what we want. I just want to know that it's never going to be worse than n squared. But for all we know, somebody could come along later with a more detailed analysis technique and show that, I don't know, that it's big theta of n log n, or something like that. So in this course, we're going to use big theta and big O that way. When I tell you a running time is big theta, that is my way of saying that there actually is an input somewhere that'll give you that performance, that'll actually require n squared operations. Whereas if I say big O, that's me saying, well, I wasn't able to prove, or I don't want to prove, like it's not worth my time to prove, that there actually is something that takes n squared, but I can certainly show you that it never takes longer than n squared. Now for the analysis itself, so I think we know enough about analysis by now to be able to conclude that this stuff here is all constant, because the wave function is constant and everything else is just arithmetic. We could do operation counting and actually number the operations, but in this case I don't need to. I know enough about how long things take, and this is uncontroversial enough that I can just say, look, this takes C operations. Who cares what C is? C is some constant. Everything inside the loop requires constant time. Everything outside the loop, so besides the loop itself, also requires constant time, so setting my bounds and then returning something at the end. And really what that's telling me is that the running time is this. It's some function t, I'm just going to gratuitously copy it out here, which is a constant times q plus d, where that's the number of operations required by the loop body, that's the number of operations required outside of the loop, and q is the number of iterations. It makes sense that there has to be something in this expression that depends on n, that depends on my input. It also makes sense that the loop, being a repetitive structure, is probably going to be one of the driving factors in the running time. It turns out, though, that in this case, based on this expression, it turns out that pretty much what we're really saying here is that this whole thing is going to be pretty much big theta of q. That is, those two constants are irrelevant, and basically the value of q pretty much determines the running time of the algorithm. So what I want to do is work out how many iterations does this loop require in the worst case. So a couple of things I'll observe about that we already sort of know to expect. In the worst case, the loop is going to keep going as long as it possibly can. We know that the loop has to finish eventually, even if we don't return in the middle, but we're not going to return in the middle. In the worst case input, we'll assume that line 12 we never reach line 12. We never actually return in the middle of the loop. So at every step, we adjust one of our bounds and go back around again. And eventually, therefore, the loop will end when low equals high. And we've written all sorts of proofs to demonstrate that. So in the worst case, the loop terminates when low equals high, when the range is narrowed down to a single value. At each step, the actual size of the range is this. And I'll quickly justify why we have a +1 there. So suppose that my current range is, I don't know, so let's do 5 through 10. Well, then the actual things in my range are 5, 6, 7, 8, 9, and 10. And there are 6 of them. right? So it's actually, the size of the range is actually 10 minus 5, all plus 1. And the plus 1 is to accommodate that it's an inclusive range. The two endpoints are part of the range. That's where I'm getting that plus 1 from. So the number of values in the range is this number, high minus low plus 1. At each iteration, I do one of these two things. So this thing here is just the value of k. So either low is set to k plus 1 or high is set to k minus 1. What I want to prove is that basically at the end of the iteration, the range has decreased in size by a certain amount. And the claim I'm going to make is that if r is the size of the range at the beginning of an iteration, then the size of the range at the end of the iteration, or the beginning of the next iteration, is at most r over 2. I'm doing a very careful dance here around the floor function. So again, you could observe that, well, okay, if the size of the range is 7, then r over 2 is, 3 points. So if r equals 7, then r over 2 is 3.5. What does that even mean? When I say at most r over 2, what I mean is that if r over 2 is not an integer, then it's at most equal to the largest integer below that number. So I actually am allowed to say r over 2, even if that might be a non-integer value. Okay, so and then the way I'm going to prove this, that the range is cut in half at each step, is I'm just going to do a bunch of tedious algebra pretty much on the two cases. So the two cases are where I adjust the lower bound and where I adjust the upper bound. All right, case number 1. If the new lower bound is this thing here, well, then the size of the range, because remember that the size of the range is always going to be high minus low plus 1, and this is the new value of low. So high minus low plus 1 would be high minus this whole business, all plus 1. And so the algebra I do there is I can observe first that if I do, so this ends up being this negative 1 and this plus 1 cancel out, so I can just ignore them. And so that means that this whole thing is equal to just these two terms here. And what I'm saying here is high minus the floor of this thing is less than or equal to this. So what I've done is I've tried to find some way of disposing of the floor function. This is a little algebraic trick that comes down to pretty much this observation here. Consider a value, let's use the variable p for this. Consider the floor of p over 2. Okay, so there's pretty much two ways this can go. So if p is an odd number, then, so if p is odd, we'll do this. It just equals p over 2 if p is even. If p is even. And it equals p minus 1 over 2 if p is odd. P is odd. So one way of getting rid of the floor function is to simply observe that I can bound it. I'm using an inequality here. I can just bound it by saying, well, look, this number is greater than or equal to the whole thing minus 1/2. And what I notice there is that means that I end up with this. And this is exactly half of the range that I started with. I do something very similar for the case where I set my new upper bound. So if my new upper bound is this number, okay, well then the new bound that I get, the new size of my range is high minus low plus 1. Okay, so there's my new value of high. And then I can again fiddle around with the terms a bit to just get rid of this minus 1 and this plus 1, and I end up with this. And I think I missed an inequality sign there. So this floor, the floor of high plus low over 2, so here's a fact about the floor function. The floor of a value is always less than or equal to the value itself. So there's a typo there. This should say less than or equal to, but it is reasonable. Oh, actually, no, wait, that's a mistake. So here I want to subtract off low. There's sort of, maybe I'll write an extra step here. This is less than or equal to high plus low all over 2 minus low. There's the less than or equal to sign. And then if I just put this on a common denominator, so it's minus 2 times low over 2, then I wrap around to this step here. So there should be maybe one extra algebraic step to show where I'm getting rid of the floor function there. And I warned you before that the floor function's a bit annoying. So even though the floor function, it turns out, makes very little of a difference to our analysis, in that a lot of people that prove results about binary search just pretend it isn't there to begin with. And actually that turns out to be fine. I want to show show my work. I want to explain where I'm getting these numbers from. Eliminating the floor function with inequalities is often pretty easy because all you have to do is to show that because, the floor of something is less than the thing itself, you can usually loosen stuff up a bit by using an inequality symbol and just get rid of the floor function. And that's what I've done here. But in both cases, what I was able to show is that the range I end up with is at most the original range divided by 2. Here, high minus low over 2 is actually less than high minus low over 2 plus 1, 1/2 of high minus low plus 1. But in either event, the claim actually holds. So no matter how I adjust my range, if it starts at size r, it ends at size r divided by 2. Okay, so what that means is that at every step I cut my range in half, or better. I mean, maybe, as in this case here, my range is actually less than half the size it started. So suppose, though, that I cut my range only exactly in half at each step. At the first iteration of the loop, the range has size n. At the second iteration, therefore, it has size at most n over 2. And I mean, you could argue that it has to be at most the floor of n over 2. Okay, whatever. We'll just say n over 2 for the sake of this being intuitive. And then at the next iteration, it has size at most. Well, that divided by 2 is n over 4. And then I've got n over 8. And I notice I'm working with powers of 2, so I'll write them as powers of 2. So 2 squared, and then there's 2 cubed. And actually, if I go backwards, n over 2 is n over 2 to the 1. And in fact, n is n over 2 to the 0. And the pattern that I noticed there is that the size of the range after I iterations is n divided by 2 to the I. It's at most n divided by 2 to the I. And so that means that if after q iterations I have low equal to high, what I'm really saying is that the size of the range is now 1, which means that n divided by 2 to the q has to be equal to 1. Now, as far as where the floor function fits into all this, well, you could argue that the floor of n over 2 to the q equals 1. Really, that just means that the number of iterations is smaller. In the case where we take as many iterations as we possibly can, where we never need the floor function, which only makes things smaller, then n over 2 to the q equals 1. And if we solve that for q, the number of iterations has to be log n base 2 of n. So that means that the improved algorithm requires big theta of log base 2 of n operations, because we saw earlier that the actual running time was c times q plus d, but c and d are constants, and so it ends up just being big theta of q, which is log base 2 of n. This is a good time, as the first time we've seen a log base 2 algorithm in the wild, that we should observe that we often just talk about this as a big theta of log n algorithm. It turns out for asymptotic purposes, the base of the logarithm, as long as it's a constant greater than 1, let's not worry about all those other weird cases less than 1, as long as the base is a constant greater than 1, which in practice is pretty much always going to be what happens. I think in this course we see a log n base 3 maybe one time, but usually it's log n base 2. It turns out if the base is constant greater than 1, then they're all big theta of each other. I will briefly justify that. So suppose I, for some reason, end up working with log n base 9 of n. Well, log n base 9 of n happens to be equal to log n base 2 of n divided by log n base 2 of 9. And if I stare at that for a minute, I can observe that what it really is 1 over log n base 2 of 9 multiplied by log n base 2 of n. And this is a constant, which means that this whole thing is actually big theta of log n base 2 of n. And so the base change formula for logarithms is just multiplying them by a constant. And so it turns out that log in any base of n is actually big theta of log in any other base of n, as long as the base is constant greater than 1. So as a result, we can just say it's big theta of log n, like agnostic, base agnostic. I guess we should talk about searching during the searching lecture at some point, so why don't we go ahead and do that. Here are 2 array-based searching problems. This one's called array search and is the general version. This one's called sorted array search, and it's one in which you can assume that the array you get as input is sorted. In both versions, you are given a value to search for, and your job is to find some index in the array that contains that value. If there are multiple places in the array that contain the value, just return the index of one of them. So the output will be some index I such that a sub I equals k, or if there is no such index, return -1. Now we already saw in the last lecture an implementation of an algorithm to solve this, and we'll see it again in a minute. The difference with the second version is simply that the array A is sorted at the beginning. You are assured that the array you're given is a sorted array. Okay, first, This function, the linear search algorithm, solves the array search and sorted array search problems. So it just looks at every single index and it tests whether that index contains the value k. And if it doesn't, and we get all the way down here, then we return -1. And this is linear time. Okay, great. So we have a solution, and it's always better to come up with some solution before we worry about trying to make our solution faster. Here is array-based binary search. And I am not going to write a proof of correctness, and I am not going to prove the running time. I guess I can assign those as exercises. Go right ahead and prove those to yourself if you'd like. I would say if I did write those proofs, you would discover that they look pretty much identical to the ones I wrote for the scale balancing problem. Because as you can see, the logic, besides the fact that I look at array elements rather than call the way function, the logic is pretty much the same. There is only really one difference, and I should point out that difference, which is that when I'm searching an array, it is possible that the element that I am searching for isn't found in the array. So I'm just going to make myself an array of size 6 here. So there we go. And suppose that I go searching this array for the value 200, and I use binary search. Well, the first thing I do is I look in the middle. Okay, I guess the closest I can come to the middle, maybe we'll look at the element 17. So 17 is less than 200, so I rule out every element up to that index. So everything from 17 all the way to the left. And then I look in the middle of what's left over. Okay, so 200 is less than 225. Which means I can rule out both of these things. And now I'm down to a place where there's only one value, only one index left. I've narrowed my range down to a range of size 1. However, unlike the scale balancing problem, it is actually possible that what's in there isn't the thing I'm looking for. With the scale, when I'm down to one possibility, that has to be the answer. With this array-based binary search, it's possible that what I get down to isn't the answer, so I have this one little bit at the end, this extra constant time extension that has to check, okay, is the one thing you have left, does that actually equal the element you were looking for? And if the answer is no, then you return -1. This does not affect the running time asymptotically, so we'll just leave it. So the running time is still big theta of log base 2 of n. Here's a question. So I was able to produce this binary search algorithm which solves the sorted array search problem. This binary search algorithm is able to solve it in log n time. So that's neat. Is there a log n, or in fact any faster algorithm for the general unsorted array search problem that's better than linear search? Can we find some algorithm that's faster than linear search, that's faster than big theta of n? Maybe it's log n, maybe it's somewhere between log n and n, but anything faster than n? The answer is no. And intuitively, it makes some sense why the answer has to be no. So here's an array of size, let's do 6 again. Okay, and I want you to tell me, is the number 17 in this array? And you don't get to know what's in any of these positions until you go and look. I would argue that because you don't know that the array is sorted, the array can be in any arbitrary order, the only way you can tell me for sure that the element 17 is not in this array is by looking at every single element. If you look at what's behind door number 1 and you see 6, that doesn't tell you whether 17 isn't necessarily behind one of the other doors. Now sure, you could be lucky and you look at one element and it happens to be 17, but that's not worst case, that's best case. In the worst case, it's always the last place you look, or maybe it's not there at all. If the element isn't found in the array, how will you know that if you don't look at every element of the array? And because the array contains n elements, you have to spend at least n operations looking at all of those elements, so the algorithm must take big theta of n time. There's the intuition. And as it happens, that intuition is correct. Every algorithm to search an arbitrary unsorted array must perform at least n operations because it has to look at every single element of the array. But strangely and sort of infuriatingly, this isn't really obvious. It's obvious that it's intuitively correct, but it's not obvious that it's formally mathematically correct. We have to write a proof of it. And the proof is, I don't know that it's the worst thing in the world, although my patience for these proofs declines a bit at this point in the course. Don't worry, we're getting to the most exciting stuff. The best part of the course is still yet to come, but we need to see what a proof like this looks like. And it does require some formalism, but we need to do it. When it's necessary to prove a fact like this is actually a very provocative statement. Saying something about every possible algorithm is a pretty big deal. We need to have a way of writing that claim down and proving it formally. Here is the theorem that I think encapsulates that claim. Every algorithm which solves the unsorted array search problem requires big omega of n operations in the worst case. Now, why do I say big omega? Why don't I say big theta of n? Well, because I'm leaving the door open that you could write a really terrible, or I could write a really terrible array search algorithm. I mean, what if you wrote an algorithm that took big theta of 2 to the n operations? Well, technically, that is not the same as big theta of n, so I want this theorem to encapsulate every algorithm that could ever exist to search an unsorted array. And there could be some out there that are just really, really bad. So all I can say is every algorithm requires at least n operations, so big omega of n operations in the worst case. And to be clear, this theorem isn't just talking about algorithms that exist. Not every algorithm that we know of, every algorithm that could ever exist. Nobody will ever create an algorithm, if this theorem is true, which it is, nobody will ever create an algorithm now or a million years from now that, when subjected to our algorithm analysis procedure, has a running time that is better than big theta of n in the worst case. Unless, of course, the algorithm is wrong. And if the algorithm is wrong, then it isn't an algorithm to begin with. And that's actually how we're going to prove this. We're going to say, suppose there exists some magical algorithm that breaks this rule, and we're then going to show that algorithm actually doesn't give us the right answer in some cases, which of course is a contradiction. And so it's still possible that there exist algorithms that sometimes require fewer than n operations. All this theorem is saying is that in the worst case, every search algorithm that is correct will have to use n operations on some input. Not every input, just on some input. And they could use more than n. For all we know, they could use 2 to the n operations. We don't care. We just know that they can never use less than n. So the way we're going to prove the theorem is we're going to prove by contradiction that every algorithm for array search must look at every element of the array. And doing so, of course, requires n operations in total. So the proof is, suppose there exists some algorithm, we're going to call it mystery search, and it solves the array search problem using fewer than n operations. So fewer meaning strictly less than n operations. So we're even leaving open the option of it taking n minus 1 operations, even though n minus 1 is actually big omega of n. We're showing strictly that it needs n. It can't take any less than n operations. We're going to show that mystery search is actually incorrect on some inputs. And of course, that means it isn't a solution to the problem. And that's a contradiction. And that'll be how we end the proof. All right, so suppose you give me this magical algorithm mystery search. One thing that's very critical in proofs like this is that I am not allowed to assume literally anything about what this algorithm does besides what is stated right here, that it solves the array search problem and uses less than n operations. I'm not allowed, for example, to assume that the algorithm contains a loop, or that the algorithm uses recursion, or that it doesn't use recursion. I can't assume anything about it besides this. And it could be using techniques that I've never heard of before or haven't been invented yet. I have to treat it sort of like a black box. I put my input in and output comes out. I have no idea how it works. It could use logic beyond the realm of human comprehension. All I know is that it apparently solves this problem using fewer than n operations. So what I'm going to do is I'm going to construct an input for it and then reason about that. So I construct an array A of size n. And the array I construct is very simple. I just set every element to be equal to its index. So I set index 0 to contain the element 0, index n minus 1 to contain the element n minus 1, and everything in between. Then I run my mystery search algorithm on this array. And I keep an eye on the array, and I watch. I don't know how the algorithm works internally, but I am allowed to watch which indices of the array it accesses as it processes its input. And since it performs fewer than n total operations, well, there are n elements of my array. So if it performs fewer than n total operations, at least one of the elements can never be looked at. Maybe more than one of them. I have no idea what it's doing, but if I watch which elements it accesses, there's no way it can access all of them. So let's let J be the index of some element of the array that the algorithm never sees. And the fact that it never sees it means that it has no idea what's behind that door. All right, so J is the index on this array, because for all we know, depending on the array that we pass in, the indices that it looks at or doesn't look at could change. We have no way of assuming which one specifically doesn't get considered. All we know is that because there are n elements, at least one of them, for any input, at least one of them can't be seen. And so we'll just say, suppose J is the one that isn't seen for this particular choice of array A. I'm now going to make a new array B. And here's the gimmick with B. B contains exactly the same elements as A in every single position except for position J. And because the algorithm never looks at position J, the algorithm won't be able to tell the two arrays apart. Okay, so I'm going to go back to the case with A, and we'll talk a bit about what the algorithm did with A. So I'm going to run the algorithm on the array A, and I'm going to search for the value n plus 1. And it should be really obvious that the value n plus 1 is not in there. And because the algorithm, of course, solves the array search problem, then if we would expect its return value is -1. Okay, so keep that in mind. On the array A, the return value was -1. Now I've made this new array B, and the array B does, as it turns out, contain the value n plus 1. You can see it there behind the fog. But the algorithm has no way of knowing that, and here's why. When the algorithm runs on the array B is identical to the array A in every place except for this hidden value J. Why do I say it's hidden? Well, because the algorithm never looked at index J on the array A. And because the algorithm never looked at index J, the algorithm has no way of knowing that this is not the array A. So the algorithm will behave the same way as it behaved on the array A when I give it my array B. And if it behaves the same way, that means that it should return the value -1. So if I run my mystery search algorithm on array B, it returns -1. And that's a way of it telling me that it couldn't find the thing I was searching for, element n plus 1. The problem is, B does contain n plus 1. I put it there. I hid it in the one place I knew the algorithm wouldn't look. And so B does contain the search value, and that means the algorithm gave me the wrong answer. And if it gave me the wrong answer, then it wasn't a solution to the problem after all. And that's a contradiction, because I started by assuming that it was a solution to the problem. Because it's a contradiction, if I go backwards to my assumption, that means my assumption was false. So when I said, suppose there exists an algorithm that solves it in fewer than n operations, that assumption is false. And therefore, there is no algorithm that solves this problem in less than n operations. And that's the contradiction we want, and that's enough to prove by contradiction that every algorithm for array search must perform at least n operations. Okay, so I've now proven that it is impossible, so not only that every algorithm abides by this, but that it's impossible to create an algorithm that, by our framework of algorithm analysis, is able to correctly search every unsorted array you give it in less than big theta of n time. I've established a lower bound on the unsorted array search problem. And interestingly, what that means, we know that linear search is big theta of n. That means that linear search is what we would call asymptotically optimal. It is, in fact, asymptotically the fastest algorithm you can come up with for the problem. There is no algorithm that is better than big theta of n, and linear search is big theta of n. That's as good as you can get. So even humble linear search gets to enjoy that status of being the best possible algorithm for this problem. This and searching an array is a pretty big deal. So I mean that's pretty good for linear search. Now it's pretty difficult to do this. Like in general, proving a lower bound on problems tends to be rather tough. We're going to do it a few more times in this course, and there are fundamental problems like sorting and searching where we can prove it because they're well studied. It also turns out that there are some problems where we would really love to prove a lower bound, but it appears to be prohibitively difficult. It's pretty easy to say if I have two different algorithms that one is better than the other, but it's very difficult to make a broad assertion that no algorithm that ever could exist is better than an algorithm that I've come up with. It turns out, as I said, that some of the most important open problems in computer science are actually related to questions about lower bounds on algorithm running times. Now, we're going to come back to this aspect later in the course, including what I'm about to describe, but if you want to know in the meantime, take a look up this. Look up the question of whether P is equal to NP. We're actually going to come back to that. But that is a huge, major open problem in computer science, and you could argue that it does actually come down to a question of whether or not a particular lower bound exists on the running time of certain algorithms. Now, the fact that linear search happens to be an optimal search strategy for unsorted arrays doesn't mean that there aren't faster algorithms for specific cases. So a common misconception is, oh, because every search algorithm for unsorted arrays has to require n operations, it's impossible for any search algorithm to require less than n operations. That isn't true. Only algorithms on the unsorted array search problem require at least n operations. We've already seen the binary search algorithm requires log n operations on the problem that it solves, the sorted array searching problem. So there's no reason why we have to give up on looking for algorithms that are faster than linear time for searching, just that we can't assume that we're going to find one for the unsorted array search problem because we've proven that that is impossible. Let's talk about one more set of problems. This is a type of search problem, but really, to be honest, I'm bringing it up because it gives us a chance to try out a variation on our analysis techniques. This problem is called test intersection, and it takes two arrays as its input, an array A and an array B. And they could have different sizes. So A contains n things and B contains m things. And the question that I want to have answered is there any element that is in both of those two arrays? I don't care if there are like 3 elements that appear in both, or whether there's one element that appears 10 times in both of them. I don't care. Just, is there any element that appears in both? If the answer is yes, return true. If the answer is no, return false. Here is what I consider a straightforward algorithm to solve this problem. I iterate over all the indices of A, 0 up to n minus 1. I iterate over all the indices of B, that's 0 up to m minus 1. And at each step, I just ask the question, is the thing I'm looking at in A equal to the thing I'm looking at in B? And if the answer is yes, then I found something that's in both. And if I get all the way to the end and I didn't find such a thing, well, then I guess it's not there, and so I return false. This bears a lot of similarity to our contains duplicate algorithms from earlier, but it doesn't admit the same improved nested loop algorithm because, unlike the contains duplicate case, the two indices I and k have separate purposes. So I can't do something like have this loop start at I plus 1 like I was with the contains duplicate case, because I do want to actually compare every index of A against every index of B if I use this pattern for my algorithm. But the question then is, what is the running time of this? I mean, I can stare at this and I can make the usual set of assumptions, like this is obviously going to be constant, so we'll say that requires C operations for some constant C. This loop here requires m iterations each time I run it. And this loop here requires n iterations. Okay, but what's the running time? Is it n squared? Is it m squared? Well, the running time, reasonably, because I have inputs that have two different sizes, I would expect that the running time does involve both n and m. And it's perfectly valid for a running time expression to have multiple variables in it. And so it turns out in this case, the running time is big theta of n times m, which depends on the sizes of both of the input arrays. Now, as a thought experiment, consider the case where B had size n. Well, in that case, the running time would be big theta of n squared, because it's just n times n. And similarly, consider the case where, actually, here's a neat one. Suppose that we know that B always has size 5. So the size of B we know in advance is going to be some constant value. Well, in that case, we go from k equals 0 up to 4, and the running time, well, n times m simplifies down when m equals 5. That just ends up being n. So it's sort of nice to have this parameterization that involves both variables, because it lets us explore the ways that the variables, the ways that the running time can change depending on the size of one input. So if one input has a constant size, then it turns out that the algorithm is actually linear time asymptotically. Whereas if the size is, in the most general sense, where the sizes could be anything, the algorithm is n times m. And we can also reason about what that means in the single variable sense. So suppose that we know that m is smaller than n. Well, in that case, the running time m times n is going to be less than, so I should be careful. Let's do this. That means m times n is big O of n squared, because m is less than n. So we can actually reason about, if we do want to talk about this and compare it to our usual classes of like log n log n squared, how does this fit in? We can say, well, I guess in the worst case, this thing is, if we assume that n is the larger of the two, then it's n squared, for example. So we can still reason about it in the single variable case, but it's very useful to have both variables in there so that the expression is sort of articulated for the cases that can arise with different sizes of inputs. And we expect that. It is actually reasonable to expect that when we have algorithms that take inputs of varying sizes, those sizes should all factor in to the running time in some sense. Now the question here, actually it's not a question, you've just been told to do this, so I suppose that must mean it's possible. Task, design a faster algorithm for this problem. Let's see if we can do better than m times n. Here's this advice that I've been giving the whole time that the slides have finally caught up to. When you want to solve a problem like this, first write an algorithm that works. Don't sit and, even if you're told to find a fast algorithm for this problem, figure out this one first. Come up with an algorithm that works, then try and make the algorithm fast. Maybe your fast algorithm looks nothing like the one you came up with at first, but having a working point of reference is very useful, both because it helps you brainstorm and also because it's really useful as a control for if you're testing out scenarios. You can verify that your new attempt matches your original easy algorithm, the straightforward one in all cases that you can test. So it does give you a bit of guidance, I guess. And it's also true that if you are given a problem and you want to come up with a fast algorithm, well, first come up with a slow algorithm, I guess. And then if you want to brainstorm possible faster algorithms and you can't think of anything, try thinking of simpler or more restricted problems. So I say to myself, okay, I don't really know an easy way of testing the intersection of two arbitrary arrays, but maybe I can think of testing the intersection of two arrays that have more structure. For example, what about this variation? Now, a solution to this problem is not a solution to the general problem. If I solve this, I haven't necessarily gotten myself any closer to a solution to the general problem, but maybe what I come up with is something that I can fit into place. Maybe I can adjust my solution to fit the more general problem. This problem says, suppose you have two sorted arrays, an array A and an array B. Now tell me if there's any element that appears in both of them. So here are two sorted arrays. And I observe that what I could do is I could look at every element of A, and I could say, for example, with the element 10, I could say, does 10 appear anywhere in the array B? And I actually could reach that conclusion by looking at the pseudocode for my earlier algorithm. I observe that this looks a lot like linear search, basically. Really, what I'm doing with this inner loop here is I'm performing a linear search of B for this element. So I'm looking at every element of B and saying, does it equal A sub I? I'm just doing linear search n times. And so in both cases, I converge on this idea that if I have a sorted array, what I could do, actually this applies even if only one of the two arrays is sorted. If I have sorted arrays, what I could do is I could look at each element of A, and I could perform binary search over B to go looking to see whether the element 6 appears in B. And I know that binary search is faster than linear search, and so if my earlier observation that this nested loop looks a lot like linear search, if that observation is correct, then hopefully subbing in binary search saves me some time, even though the problem I'm solving is a little bit different now. So I end up with this pseudocode. I take my two arrays A and B, which are assumed to be sorted, and then I loop over every element of A, and I just go searching in B for it using binary search. By the way, this is the specific binary search function that we saw something like 40 slides ago. And then if I find the element, so in other words, if it doesn't return -1, then I return true, and if I get to the end and I haven't done that, then I return false. Okay, but this doesn't actually solve the original problem. The problem was to solve the test intersection problem, which doesn't involve sorted arrays. So what do? I have a solution to a related problem, and I realize, wait a minute, I can always sort one of my arrays. Actually, I should talk about the running time quickly. So this algorithm's running time, there are n iterations of the outer loop, and we know that the running time of binary search is log of the size of the array you're searching. But the array we're searching here is B, so it's actually log base 2 of m, which means the total running time is n times log m, which is definitely an improvement over n times m. If I want to solve the general problem, one way of doing that would be to sort the array B. And we know, because I basically declared it by fiat in a previous lecture, that sorting is n log n. So B has size m, so sorting would be m times log base 2 of m here. And so I sort one of my arrays, and then I leverage my algorithm to test the intersection of sorted arrays to perform a series of binary search operations. So I just adapted my binary search strategy for the unsorted version of the problem by first sorting the array as a pre-processing step. If I stare at this a bit, the running time is basically just the running time of the sorting followed by n times log m. And so we can express that in a couple of different ways. Notice that I'm using a big O expression here. So the expression for running time, well, okay, this takes m times log base 2 of m, and this takes n times log base 2 of m. And so the total running time is, at most, this. And you can see I'm using big O. And the reason for that is that all we've been told so far, that theorem I just presented out of nowhere that tells us how long sorting takes, and don't worry, we're going to prove that theorem ourselves eventually. That theorem told us that we are able to sort arrays in m log m time. It didn't tell us that we can't do any better than that, so for all we know, there is a faster way of sorting B. So I'm not allowed to say that this new algorithm is big theta of this whole thing, because for all I know, there might be a way of getting that sorting time down a bit. So instead I just say the algorithm is big O of m log m plus n log m. I can also rewrite that expression as m plus n times log base 2 of m, just to make that clear. All right, so I now have this algorithm. This is faster than n times m. I actually think it is decisively faster because log m is way less than m as m begins to get large. So here's a question. And this is just to reason, because asymptotics don't tell us everything, but also to reason about this situation where we have multiple variables. Suppose you have two input arrays with different sizes, and observe that really there's A and B. There's nothing special about A versus B. They're just two different arrays. And that is to say, if I wanted to, I could swap them without really changing anything. So the question is, why is it that I've decided that B is the one that I sort and then use the binary search algorithm on? Why wouldn't I do that with A? Suppose that A and B have different sizes. So this is a question to think about later. Which situation is faster? If A is the smaller array or if A is the larger array? So something to contemplate, a good way of sort of critically thinking about algorithm analysis. And then one other thought experiment to leave you with. We talked about this related problem, test intersections sorted. Actually, I'll just go to the question here. This was a problem that we solved in the margins as a way of getting a solution to the problem we actually cared about. But while we're on the subject, see if you can think of an algorithm that solves this even faster. So the one we came up with was m times log base 2 of, it was actually n times log base 2 of m. And so this is definitely not as fast as that, n plus m, big theta of n plus m. Big theta of n plus m is really good, because we already know that searching problems, searching unsorted arrays, we can't really expect to take any better than linear time. And this, when we're working with arrays of size n and m, this expression here is linear time, because the variables n and m only ever appear as in linear functions. And so the question here, the exercise here is, see if you can come up with an algorithm for the case where both arrays are guaranteed to be sorted, where the worst case running time is n plus m. And if you're stumped on that one now, give it, 4 or 5 lectures and see whether once you've learned about sorting algorithms, there's something you could use to do the trick. Now, before we get to sorting, we've got a couple of other things we have to talk about. I want to spend some time talking about data structures for a bit, things like arrays and linked lists. Most of that's just going to be review, but it's good to talk about that. And then, before we really get into what I consider to be the best part of the course, we do have to talk about one tiny thing which we haven't really spent much time on yet, which is sort of a big deal, which is we have to talk about recursion.